All right, so I think the streaming has been started also. So with this, we will begin. So today I plan to discuss the part where we've discussed the structural graph coverage criteria. So that is actually the first 4 weeks. Week one was mostly introduction. I think we've covered it in the initial session also, and there are recordings from the previous terms also wherein we have discussed all these topics. So for today, I would rather go discuss some of the specific things from within the structural graph coverage criteria. Okay, so this is what we are going to look into, and then fundamental graph algorithms. We have discussed BFS, DFS only, so I presume that most of you would be familiar with that. So for now today, I'll not be discussing that. Maybe I'll move to the simple parts, prime parts, and the coverage criteria that is there. Okay, maybe we can do one example also, but I'll see. I promise I'll do one example as well. Okay, so let us begin with this structural graph coverage criteria. I hope the screen is visible. Can anyone of you please confirm if the slides are visible?
Yes, yes, it's visible, sir.
Okay, thank you so much. All right, so a little bit of overview as to how do we do that. Okay, so the one thing that I'd like to just point out is that when we are going to test software, so it is source code, right? So what we do is we are going to model the, and here we are saying artifact, right? Software artifact. But in general, the discussion is going to be predominantly about source code. So some of these techniques that we are going to discuss are applicable not only to source code, but other constituents of software, which could be design elements or requirements as it says, and some other things that could be there. So these techniques could be applied to them also to test them. But for our discussions, I think we are going to be dealing mostly with source code. Okay, and that too in the Java programming language. All right, so once we try to test the software artifact, or in this case source code, we'll have to have some kind of a model, to run our algorithms on, right? Because this coverage criteria, the way we compute those test requirements and then figure out the test paths, and then we try to execute those test cases that are there, right? And then so there has to be some kind of underlying model by which we can represent the software under test, or maybe a portion thereof, maybe a method or something like that. So in this particular week, like this is I think started from week two only, the later part of week two, and goes up until week three also. So we have data flow and so on. So it is all based on the graph model of looking at software. Okay. So in these discussions, we are going to model the software artifact as a graph, particularly a control flow graph. Okay. CFG for short. And then we run these, uh, you know, uh, uh, we execute these tests on the CFG itself. So that's what we are going to do. So therefore, structural, right? Because the CFG, the control flow graph, tries to model the, the control flow, as it says, of the program under test, and therefore it kind of captures the structure of the underlying code. So if we do tests on the CFG that is there, what we are trying to do there is to test the underlying structure of the source code itself. So that is the general idea. With this in mind, we'll move forward and look into various criteria for graphs that are there. So, so you might understand what a graph looks like. Okay, so the CFG is basically, uh, you know, the nodes and vertices are there. I hope all of you are aware of what nodes and vertices are. Okay, so the each of the execution, the points of execution, or maybe the statements in the source code, may be represented as a node. So when we reach a node, there's some sort of computation happening. So let's say I'm going to declare one variable, right, and assign it to some value, right? So that might be one node in my graph that is representing some kind of operation. Okay, and then there are edges. We'll see examples soon enough. Okay, then there are edges in the CFG that represent the decisions that are taken. So for instance, in your program, if you have if conditions, then depending on the value of the if condition that is evaluated at runtime, if it turns out to be false, then you follow one branch of the CFG. If not, then you follow the other branch, right? So therefore, edge is representing that kind of a division. Okay, so basically you follow the path depending on whatever the condition turns out to be. Okay, so then edge coverage is there and edge pair coverage and so on. Okay, so node coverage basically says that we are going to visit every node that is there in the CFG. Similarly, edge coverage says that we are going to visit, meaning you have to have a path that goes through the edge. That is what it means to cover. Okay, when we say we wish to cover something, it means that we wish to visit that. We have to have a path such that that particular node or edge is visited. Then we say it is covered. Okay, so edge pair is that we are covering pairs of edges and so on. And then we have path coverage that is in general for any graph, any CFG that is there. Okay, so for path coverage, we have several other things inside of that. So we have complete path coverage, prime path, complete round trip coverage, and simple round trip coverage. So in particular, today I'm going to specifically discuss prime path coverage because that is an interesting one. Okay. So yeah, node coverage requires that test cases visit each node, as I said in the graph one. So that is okay. Uh, All right. So and then test set T satisfies node coverage on graph G if and only if for every syntactically reachable node. This is said because there can be unreachable statements within the source code, no? So it might not be possible to satisfy one condition and therefore you cannot reach that portion of the program ever. In that case, it will not be reachable at all. Right. So that might happen. So to be precise, we have said that every syntactically reachable, whatever is reachable, meaning whatever could be reached, and then you reach that, right? So you visit that and then we say that that is covered. That basically satisfies node coverage. Okay. And the test requirement for so there are three things that I wish to be clear about since we are talking about this. One thing is test requirement. Okay, so you have to be clear about these terminologies. Test requirement is dependent on the coverage criteria that is chosen. Okay, if I wish to do node coverage on a CFG, and test requirement, by the way, is a general term that we're going to use throughout the term. So apart from structural graph coverage, or even apart from the things that are based on graph models, there are other testing techniques within which we also use the same terminology, saying test requirement, right? But the test requirement differs as to uh, depending on what coverage criteria you wish to achieve. So if you wish to do on structural graph coverage, then there are several test requirements. If you want to do if you want to do other models of testing techniques, then in that case other test requirements are there. So that we will see later. But for now, we'll look into structural graph coverage criteria only. And in for that, so for node coverage, we have the test requirements. It says that we have to have each reachable node in the graph that is the CFG. Okay, so that differs actually depending on what coverage criteria we have. Edge coverage again says that we have to cover each edge that is there. One thing to note here is though that this requirement for edge coverage is basically each reachable path again of length up to one, meaning edge coverage can also be achieved when there are no edges. So let's say there is a CFG. Well, technically there can be a CFG when there are no edges. So there's only one node there. Okay. So then if you wish to do edge coverage in that, then we can still do that even if there are no edges. So therefore, it says up to one rather. So the path, the path length starts from zero. If you say path of length zero, then that is basically the node because you are not going anywhere. So you are at the node, and then there is no path, extending from that. So therefore, that has a path of length zero. So you are still there. So that will be that can still be edge coverage when you consider paths of length zero. Okay, and so on. So paths of length one is basically your edge. The actual edge is of size one, right? So length one, and then you go to next node, and then from that you continue following like that. Okay, edge coverage is slightly stronger than node coverage because it requires you to have visited the edges that are there. So for example, if there is an if condition in the program, right, then what happens is that you'll have two edges. Maybe I'll show you example soon enough. Okay, so if you want to do edge coverage, then you have to visit the edges for both branches of the CFG. Okay, so you are maybe at some node, and then there is this if condition that is there. So if the if condition turns out to be false, then you follow one edge. If it turns out to be true, then you follow another edge, right? So if you wish to cover for, if you wish to satisfy rather edge coverage, then you have to make sure that you visit both edges, thereby accounting for both possibilities that may arise, right, during the execution of the program. Okay, yeah, this part of while length up to one is already mentioned, right? So because so as to be able to cover with only one node and no edges. It's a trivial case, of course, but we have to define. Yeah, I think there is a raised hand. Please go on if there's any question. Yeah, Anubam, go on, please.
So can you please tell me that from where we get this slide and is this available as a recording or not?
Yeah, this session, first of all, is being streamed on YouTube, so you should be able to revisit it later if you wish to. And the other thing regarding lecture slides is this one. So we have shared it, in fact, with the
So
students, I think.
can you please give me the link? So actually I
Yeah,
haven't got the link.
yeah. Let me paste it in the chat. You may take it from the chat, please. Okay,
Okay,
just
sir.
paste it
Yes.
here. Yeah. All right. Okay. Shall we move forward? Any other thing that you
Yes,
wish to
sir.
ask?
Yes. No, sir. It's okay.
All right. Sure. Fine. Thank you.
Excuse me, sir. Is this class is daily is running in daily session or just for week? I think your mic is off, sir.
Oh, okay. Sorry. Am I audible now? I'm sorry. I think I was speaking on mute.
Yes, sir. Yeah, right now.
Okay. Yeah, so I was talking about this one. It was mentioned that we are allowing for length up to one. Okay, so it says that basically to allow wherever we don't have edges and we only have one node, so then also we can do edge coverage, right? I mean, it's a trivial case, of course. I might have said it earlier also, but I think I was on mute. I'm sorry. So, and therefore, you know, so and the other benefit of having that is that when you have length up to one, it allows edge coverage to subsume node coverage, as it says. So what happens is that subsumption, this idea of subsumption is something that we're going to see a lot in the following weeks also. So the idea of subsumption is very simple. It says there is a test requirement for me, there is a test criteria that I wish to satisfy. Okay, so if I am satisfying one criteria and at the same time I say that there is another test criteria, let's say T2, so, and I say T2 subsumes T1. Okay, then if I am satisfying T2, then it follows that T1 is also satisfied. That is the idea. Okay, so in that way, if you think about it, edge coverage, since it visits every path, each reachable path, okay, meaning all the edges that you have, then it is implicit. You may understand that it will also satisfy node coverage, right? Because we are visiting every edge, thereby visiting every node also in that process, and therefore covering node, satisfying node coverage also, therefore subsuming that. Okay, so you have to be careful about that. And this is general enough. So maybe in other models also of modeling the software, we will see that subsumption may apply in certain criteria. We may see that later. All right, so a little bit of example is given here. So it says for node coverage we have 1 to 3, of course, because for node coverage you the test requirement set basically says that you have to visit the nodes. Note that here we are not talking about how are we going to visit. Okay, so there is a difference between test requirement and test path, and that is what I wish to discuss today also. You have to be careful about that. Okay, test requirement just says that what are the things that I need to visit in general in the in the graph coverage criteria at least. Okay, what are the things that I need to do? What are the things I need to visit in case of graph coverage criteria in case of CFG? And the test path says that what are the paths that I'm going to follow, or the test path, a single test path tells us how are we going to do that. Like we're going to start with the initial node and end in the final node. So the test path, the distinction is that a test path must always start with the initial node and must always end in the final node. This double circled one, this node is basically known as the final node. Okay, So the idea of a test path is that it should start in the beginning, because you understand this is like a program, right? So we are modeling a program here. So program must start from one single place, right? It just starts from somewhere and it always ends somewhere, right? So therefore, this idea of following the path basically corresponds to an execution of the underlying program that is there. Okay, so we start here and then maybe do something at node number 2, and then we move on and complete the execution at 3. Yes, please.
So what is TR denotation that TR denote for?
TR is test requirement. Okay.
Okay, test requirement.
Yes, and test path is basically the path that, so test path is the path that you're going to follow. Test requirement says that what I need to do, what I need to satisfy. So for node coverage, the test requirement is all nodes, right? Because I need to visit all nodes. So therefore, it is obvious that we'll have all nodes there. Okay. So in this graph, we have 1, 2, 3. So then TR is that. And again, note that test requirement itself does not state how are we going to achieve it, or is it even feasible or not. Okay. Test requirement may say something that, okay, I wish to cover so and so paths, maybe in case of specified paths. Maybe you say that I wish to do so, that part I wish to follow. Maybe I can say in test requirement that maybe that I wish to visit from 1 to 3 to 2, but that is not feasible, right? So that will not be a test path and that cannot be done. But the test requirement nonetheless can still be there. But again, we have well defined criteria for all these things that are there. So in general, the test requirements are feasible, but in some of the other models, like for example, for logic coverage criteria that you might see in week 5, some of the requirements may be there that are not feasible also. Okay, that might not be very observable in the case of graphs, because all the paths that we give, most of them will be reachable only. So you might think that the test requirement also is always satisfiable. Okay, but it might happen in general. I'm telling that there might be test requirements that are infeasible, particularly in logic coverage criteria. In week 5, we will see that. Okay, so maybe we'll see that next week. Okay, so again, so test requirements for node coverage is basically your nodes. So 1, 2, 3. It's a test set actually. Rather, it's a set of requirements that are there. So therefore, this notation. Okay, and the test path is the actual path. So this is the sequence you are going to follow. Okay, so test path says that to satisfy node coverage, I need to start from 1, because of course I need to always start from the initial node. Then I go to 2, then I go to 3, and therefore in that process I have covered for every node that is there, right? 1, 2, 3. So therefore satisfied node coverage. But note that 1, 2, 3, this test path does not satisfy edge coverage. Okay, because how many edges are there? 1, 2, and 3. Three edges are there except the initial this thing. This is just an arrow notation, so we'll not consider that as an edge. But the actual edges are 3 edges there. So if I start from 1, I go to 2, and then I go to 3. So that is okay. These two edges, 1 to 2 and 2 to 3, I have covered. But 1 to 3, I have not covered, right? From 1 to 2 to 3. Not 3. This edge is not covered. And therefore, this test path 1 to 3 will not actually satisfy edge coverage. So what do you need for edge coverage? So edge coverage says that I need to cover for every edge that is there. And you know how do we describe edges? The from node, right? So from and to, that kind of a notation is there. So from 1 to 2, so we have 1 comma 2. This is one edge. So 1 comma 2 is one edge. 1 comma 3 is another edge. 2 comma 3 is another edge. Three edges are there. Therefore, three test requirements are there for edge coverage. Okay, so then I know I need to cover for this, right? And then I have to figure out how do I do that. Like how do I satisfy this edge coverage? So then I have to figure out the test paths. So one test path could be 1, 2, 3. So 1, 2, 3, 1. So 1, 2, 3. This test path covers for the edge 1, 2, because I followed this. That is okay. It also covers for 2, 3. The edge 2, 3, because 1, 2, 3 covers for 1, 2, and 2, 3. So the idea of covering is that you just visit it, right? So since I've done 1, 2, 3, it means that I have visited 1 to 2 and 2 to 3 also. So that is covered. And regardless, 1 to 3 was not covered, like this one, from 1 to 3, right? This part was not there in this test path. So therefore we need two test paths, right? And you might imagine that it is not possible to cover for edge coverage on this particular CFG in less than two paths. So the minimum number of test paths that you require for edge coverage on this particular CFG has to be 2, right? Because there are there's no other way. You have to have two paths at least, right? So 1 to 3, and then one from 1 to 3. Okay, so yeah. That is what happens.
So can you please explain this test path of edge coverage? I haven't understand that why it is that 1, 2, 3 and 1, 3 is there.
Right, right. So if you, so you understand that these are test paths, right? The set of test paths. So
Yes, sir.
there are two test paths here. Okay. So one test path, this one, 1, 2, 3, this first part. I think my highlights are visible. I hope
Okay,
it is.
yeah, yeah, yes, sir.
So yeah, so it covers for these two edges, right? 1 to 2 and 2 to 3. I
Okay.
followed that. But what about this test requirement of 1, 3? This we have one more test requirement, right? That I say that I require that this edge also must be followed, right? 1, 2, 3 from 1 to 3. This one from directly from starting from one and ending at three. That edge is there, right? So
Yes, sir.
how do I cover for that? Therefore, I need another path, right? You
Okay.
understand? And
Okay.
from three, you cannot go anywhere else also. So you
Yes.
have to have, and you of course start from the initial one. So the again, remember for test path, you always start with the initial vertex, always end at the final vertex. You cannot end in between, and you cannot start from anywhere else. Okay. So for example, you cannot start from two. You have to start from one, and you have to always end at three for a test path. Okay, not that for a test path, not for
Yes.
requirements. Okay,
Yes, sir.
requirements are just saying what you need to achieve, what you need to cover for. So for example, you start from 1 to 2 to cover for 1, 2, like this edge is there. But yeah, and so the idea is that if you start from 1 go to 2, then the edge 1, 2 is covered, and then whatever I follow is up to me. I'll say that that part is covered. So 1 to 2 is covered. Rest of the path could be anything else. As long as I am visiting that particular edge or particular node which I wish to cover, then I'm okay with that. Okay. So that is the
Okay,
idea.
sir. Yes, sir. I understand.
All right. So once you understand this is like a general thing that is there in structural graph coverage criteria. So therefore, all rest of the coverage, rest of the criteria rather that are there basically follows from that. So then again, so H pair says that you have to cover for two, like pairs of edges. So for example, so it'll be something like that. You don't only follow one edge in the. I'm talking about the requirements, right? You also continue one, one more edge from that. So therefore, it becomes pair of edges. So for example, I start from one. Okay, so 1, 4, and from 4 to 5. So this is like a pair of edges. Two edges are there, right? So three nodes will be there, and two edges will be there in between them to connect them, right? So 1 to 4, and then 4 to 5. That is one edge requirement for edge pair coverage. So it covers for edge the pairs of edges 1, 4 and 4, 5. Similarly, 2 to 4 and 4 to 6. So 4 to 6 is also must be there. Yeah, this one, right? 2, 4, 6. This test requirement is actually covering for these two edges from 2 to 4, and then from 4 to 6 to these two edges. So all combinations basically you have to do. So start from 1, 1 to 4, then 4 to 5. Then you see from anywhere else. Can we go from one? No, I think we can go anywhere else from one. So then we go to two. From two we can go to four. So 1 to 4 to 6 is one case. 1 to 4 to 5 is another case, and then 2 to 4 to 5, 2 to 4 to 6, and then from three. So 3 to 4 to 5, 3 to 4 to 6. Okay, I think nine requirements are there. One, two, three, four, five, six. Okay, six requirements. Yeah, two nodes are on this side, right? So therefore six requirements, because for each of the nodes you have to cover for two paths, right? Two two edges. Therefore six. Okay, and if this happens in this particular case, it turns out that uh you know you can have test paths also. Apparently, uh this was supposed to be initial node also, but the arrow is not there because we have to start from the initial node. It says test paths are same, but if that happens, then 2, 4, 5 has to be a test path. This ends at 5, so that is okay because that's the final node. So we can end here. That is okay, but it is not mentioned whether we can start from 2 or not because this arrow above 2 is not there. But we assume that it's initial node also. So then in that case, yes. So you start from 2, then you go to 4, then you go to 6. But if it does not, like if it does not start from, if it only starts from 1, then you cannot have 2, 4, 6, right? Because you cannot cover for that in that case because 2 is like disconnected in that way. How do you reach 2, or you start from 2, right? So you have to start from 2 in this case. But in most of the cases, whenever you are going to start from a node, above that there'll be an arrow indicating that that is the initial node from which you can start. Okay, so in this case the arrow is not given for 2 and 3. Hopefully that will be corrected later. Okay, so that is the idea of edge pair. Okay, so it is like you are going like this. So path of length 0 is your node because you're not going anywhere, so it makes sense to have a path of length 0. because I have not traveled. So therefore, node itself. So node coverage is path of length 0. And then you go to edge coverage. So that is path of length up to 1. Okay. So that subsumes node coverage because, up to 1 includes 0 also. So therefore, node coverage is subsumed by edge coverage. And edge pair coverage, then it says path of length up to 2. Okay. So it says from 1 to 4, and then I'm going one step ahead. So 1 to 4 and then 4 to 5, like that. Pairs of edges. Okay. And then you can understand that if you do edge pair coverage, then edge pair coverage actually subsumes edge coverage. Because you're covering for edge of pairs of, every pair of edge. So of course, all edges are covered. It subsumes it, right? So then again, that is how it covers for it, right? So it says length up to 2 ensures edge pair coverage holds for graph with less than 2 edges. Yeah, it might be that you only have one edge, then how do you do edge pair coverage? So therefore we say up to 2. But regardless of this fact, actually, because you are covering for every edge that is there by covering all pairs, so therefore every single edge that you have covered already, therefore edge coverage is subsumed by edge pair coverage. Okay. So this is how you move forward. Okay, and then there is this thing called complete path coverage. Okay, the extension of edge pair is to consider all paths of all lengths, right? So this, unfortunately, is an infeasible test requirement because in your program there can be loops also, right? So you have for loop, while loop, do while loop, and so on. In that case, if we model that program as a CFG, you're going to get cycles in that. Okay, so some node will be there, from that you go back to some other node, so therefore it creates a cycle. We'll see an example soon enough, right? So therefore, if so that kind of creates an infinite length path, if you think about it, right? So we can iterate how many ever times I wish to, and I can keep going in cycles on and on forever. So that creates a problem, and therefore complete path coverage is infeasible in general. Okay, because you have to stop somewhere. So you specify something like you say that, okay, I want to do for edge pair coverage, and that is okay because you're going to stop at that length. But if we say all paths or complete path, that is possible, it is not feasible in general, especially if you have loops in your program, which is quite typical, no? So in usually all programs do have loops, therefore it becomes infeasible. Specified path coverage is basically whatever paths you specify, as I was explaining earlier also. So I just say that I wish to do so and so paths, so that will be your TR. you know the user is basically saying that I wish to go from this to that and so on, right? And that becomes your test requirement. Okay, so again, quick recap. Node coverage is path of length 0. You have to just make sure you visit every node that is there. Going forward, edge pair coverage says that you have to, rather there is edge coverage before that. Yeah, so edge coverage is described here. Edge coverage says that you have to cover every edge. That is okay. And edge pair coverage says you have to cover pairs of edges, that is length up to 2. That is again okay. And then you have complete path coverage that says all paths, which is infeasible. This is understandable also, I hope. And specified coverages, it just says whatever paths has been specified, a set of paths is already given to you, you're going to just follow that. Because in this case, there's no specific need to compute the paths and so on, right? Because the paths are given, you know, you have to follow. So you just follow that path. Okay, so I hope it is clear. Yeah, so this is what happens. So node coverage, the TR is how many edges are there in the CFG? 7, right? So from 1 to 7. 1 is the initial node, 7 is the final node. So test requirements for node coverage, but it will be all your nodes because I wish to visit all nodes. How I'm going to visit is a different question. TR is just saying that I wish to visit that, therefore I cover for it. Node coverage. Okay, so all the nodes. And then there can be multiple different test paths that are possible, right? To cover for all the nodes that are there. So that is okay. There can be different test paths, but as long as you are satisfying or reaching the test requirement criteria, then in that case, that's okay. Your test path was said to have satisfied that requirement. Okay. So in this case, for example, it says 1, 2, 3, 4, 7 is one path. Okay, and so 1, 2, 3, 4, 7 covers for these many nodes, right? So 1, 2, 3, 4, 7 is covered, and then 5, 6 is remaining. Again, we have to start from the initial node, therefore we are starting from that, and we have to end at the final node, so that's okay. If you start from 1, then you can go to 2, 3, 4, and then from 4 you cannot go anywhere else. You have to go to 7, right? From 4 you cannot jump anywhere else, so you have to go to 7, so that's okay. But we still miss 5 and 6, right? So in that case, therefore we need another path in this case also. mean, we cannot have one path that covers for everything, because if I start from 1, I go to 3, and then I go to 5, and then maybe I go to 6 and then come back to 5, that's okay. Then either I keep doing this cycle or come to 7, and that'll end the, you know, end the path. So in that case, I'll still miss out on 2 and 4, right? So therefore these two paths are required for node coverage. Okay, edge coverage, similarly, all the edges that are there. So 1 to 2, 2 to 3, 1 to 3, 3 to 4, 3 to 5, 5 to 6, 6 to 5. Okay, make sure you cover both ways when you are doing for loops. Okay, so 5 to 6 is a separate edge, 6 to 5 is another separate edge. Even if it is mentioned, as one edge, please do make sure that you cover for both sides. Okay, and yeah, and then 5 to 7, 4 to 7. So that's what you have here. Yeah. So 1 to 2, 1 to 3, 2 to 3, 3 to 4, 4 to 7, 3 to 5, 5 to 6, 6 to 5, 5 to 7. And then the test paths again are, so 1 to 3, 4, 7. Let's see how many edges are covered. 1 to 2 is covered, 2 to 3 is covered, 3 to 4 is covered, and 4 to 7 is covered. So yeah, maybe I'll write. Yeah, okay, I'm not able to annotate here, but yeah. So this one covers for 1 to 2, 2 to 3. So 1 to 2, 2 to 3, and 4 to 7 is covered. Again, you have 1 to 3, that is remaining this one, and uh, right, 1 to 3, and then 5 to 6, 6 to 5, and 5 to 7 remaining. So therefore you have another path that does the that basically visits the remaining edges, that makes use of the remaining edges. In this case, you see the test paths for node coverage and edge coverage actually collide, meaning uh, it's the same thing, right? Both are the same. So in this case, maybe if one question asks that, okay, you have been given this set of test paths, do let us know what all coverage criteria satisfy. So in this case, you can say it satisfies node coverage as well as edge coverage, because you see it is happening in this case. And by the way, edge coverage anyhow subsumes node coverage, right? Regardless, because it subsumes that, right? So if you are covering for edge coverage, node coverage is implicit in that. But there might be a question that says, what is the minimum number of test paths that you require, right? It might happen. So it might be that for edge coverage you need two paths, as in this case, but maybe on the same graph it might be that you need one path only for node coverage. It can happen, right? So you have to be careful about that. If it asks for the minimum number of test paths, then you have to figure out, like, is there a way to minimize it? Okay, like, can you do it in one path and so on. Edge pair coverage, again, we are covering for, like, we are having test requirements for all the edge pairs that are there, again similarly, and so we have to have these many test paths for that. One may verify it. Okay, and then complete path coverage is infeasible because you have a loop here, right? So this much is fine. So you may do 1 2 3 4 7, 1 2 3 5 7, and so on. But as soon as you hit this 5 to 6, 6 to 5 loop, you keep on doing this uh, forever in some sense, right? So therefore it becomes infeasible, because you have to start, this is the set, right? You have to have a finite set to be able to execute those tests and so on, right? Yeah, infinite number of paths, and hence complete path coverage is infeasible. That is okay. Yeah, it says about one more thing. So when we have loops, what do we do about them? Okay, like, it's okay that complete path coverage is not possible, but what do we do about loops? Can, like, once we hit that 5 to 6, 6 to 5, shall we, you know keep going like this, or how do we break out of the cycle? We have to have some criteria, to be able to specify that. So the idea then becomes that you set a number of iterations that you wish to do. Like, for example, maybe I want to visit 2 times and so on, something like that, to be able to stop the cycle, right? Right. So it says loops will have boundary conditions and repeated executions. Effective test cases will not execute the loop for every iteration, meaning you generally not need to do. So there is a list, maybe there's a huge list, on which you are iterating, maybe computing the average, or maybe for computing the sum and so on. So what happens, while we are testing for it, maybe you do it for some iterations, need not do it for all iterations, because it might be that all iterations are not possible even. So you do it for some iterations, and then that suffices. Let's say it will be specified depending on the coverage criteria that is mentioned. Right. Yeah. So there's this criteria that is mentioned in general. What should happen? is that execute the loop at its boundary conditions, right? So maybe you, there can be three possibilities, right? You don't execute it, meaning you don't get inside the loop. You avoid the cycle completely. That is one case. The other case is that maybe you execute it once, you know, and that is about it. Maybe you maybe you iterate twice, but that's okay. Maybe you try to do it for two iterations, that is okay, but then boundary conditions have to be covered. So you make sure that you execute the loop once at least, because you have to make sure that that flow is correct. Maybe some bug is there in the loop, right? So you have to visit it to be able to realize that, right? If you don't execute the loop at all, then you don't know whether something is wrong there or not. So you have to at least do it once, and then you have to skip also, because you have to think about it, right? Maybe if the input is not provided, what happens? Does the program crash or what happens, right? So you have to be careful about boundary conditions. So the general convention is to skip the loop, make sure they skip the loop once, and then execute it once also. So these two things that can be covered. Okay. So the notion of prime paths then basically came into existence for working with loops, because we will see this part is important. There might be questions based on this in the exam also. So before we get to prime paths, there's this notion of simple paths that you will understand. So be careful with this definition. Okay, you have to remember this. So it says a path from node I to node J is simple if no node appears more than once, meaning there should not be any repeats. But it says one more thing. Okay, except possibly the first and the last node. Okay, so this might be slightly confusing, so I'll just clarify this part. What we mean to say here is that when you have a loop, okay, the first and the last node have to be the same. So for example, if I were to go back, I am at 5, I go to 6, I come back to 5, then again it's simple, because I started at 5, I went to 6, and then I came back at 5, even though there is repeat, right? So the number 5 is basically at the first node is number 5 in that path, and the last node is also number 5. That is okay, that is allowed. So if both nodes are same, with which you begin and you end, and those two are same, and those two, that is the only repeat that is there. But internally there are no other repeats, right? So there should not be any other repeat in between, then it ceases to be simple. For a path to be simple, it is either have no repeats completely, or if there is a repeat, then the first node and the last node should be the same. Meaning basically, it is trying to model a loop. That is how a loop will look like, right? You go once inside that, and you follow the complete loop, and then you come back to the starting point. That is like a cycle. So that remains simple. But if you repeat that again or do something else, then it ceases to be simple, because then in that case we'll be having repeats which are not the first and the last nodes. We'll have repeats in between. Okay, so that the node cannot appear in between multiple nodes. Right, and then no internal loops. That is, a loop itself is a simple path, but internally there should not be any other loop. Okay, and then so extending this notion of simple path, prime path, and maybe I'll do example also. Prime path is a simple path that does not appear as a proper subpath of any other simple path. Basically, it says the longest simple path. Okay, that is the simplest way to remember this. The maximum length simple path that can be there is basically a prime path, beyond which you cannot, like, we cannot extend it beyond that. So that is your prime path. Okay, so we'll see this one. Right, so we have this. Maybe I'll make it smaller. Right, so all such paths are simple. Like for example, 1 2 4 1. Again, you see, so one is repeated, but one is the first and the last. But in between there is nothing, no other repeats and so on. So that is okay. And remember one more thing: if it is something like 1 2 1 4, 1 2 1, again it will be wrong, right? So internally there should not be any repeat. It's only that one, the first one and the last one should be the same, and that is the only repeat that is allowed. Okay, so then it will be considered simple. So 1 2 1 2 4 1, right? 1 3 4 1 and 2 4 1 2, and so on. You keep doing this. You basically start from one, right? So, to be able to compute all paths, you start from somewhere. You have to start from somewhere, right? So maybe you start from one. You go in order. So you start from one, and then you compute all the simple paths, and then among those paths which then cannot be extended further are your prime paths. So for example, we do something like this. We start from a simple path of length 0. So maybe I'll get back to this and maybe try doing this one, because that'll be easier to understand. I'll try to do this, you know, and annotate it also. But before that, let me just quickly cover the other coverage criteria. Okay. So, and then for prime path, then, so node coverage says that we have to reach every node. Edge coverage says we have to reach every edge. Edge pair says for every edge pair you cover. And then we have complete path coverage, which is not visible. Specified path coverage, you understand what that is. If someone has specified those paths, you have to visit those paths. Then prime path coverage, the test requirement is, you have to be careful about that. The test requirement set rather, for prime path coverage, for achieving prime path coverage, is basically all prime paths that are there, in G. So once you compute the prime paths, and we'll show you how to do that, your test requirement is basically that all the prime paths become your test requirement. So the number of test requirements for prime path coverage is basically the number of prime paths in that graph. Okay, and this by definition, prime path by definition ensures that loops are skipped as well as executed, because we are allowing for one iteration, right? By having this notion of first and the last being same, so we allow it once, right? So therefore we visit it once, one iteration is allowed, and we skip it also because uh, we we might not get into the loop, therefore we don't iterate. And therefore when once we do prime path coverage, it is ensured that loops are also skipped in one of, if it is possible, like if in the CFG it is possible to skip the loop, then you will have paths such that test paths such that those test paths skip the loop, meaning they don't visit that cycle. And there will also be paths, right, that actually execute the loop once. Okay. Yeah, and by touring all paths of length 0 and 1, meaning all nodes and all edges, it subsumes node and edge coverage. Okay, so prime path actually subsumes node and edge coverage also, but it may or may not subsume edge pair coverage. That depends on the underlying CFG that you have. For some CFGs it may, for some CFGs it may not. But if a general question is asked, does prime path coverage subsume edge coverage? You have to say no. Okay, not always. Okay, and then we have, yeah. So there we have shown a difference between why edge pair coverage is not actually subsuming the prime path coverage. So in this case, you see what happens for edge coverage. Actually, uh, we have to visit the self loop also. So you see 1 2 2 is also there, right? So from 1 to 2 and then again to 2. So that will be your edge pair. So itself, like it is repeated twice. So that is again edge pair, but uh, we are not having that in the case of prime paths. Okay, so therefore you see it does not subsume. Okay, maybe we will do this one also, right? Let me discuss one example maybe before going to
Yes, sir.
towards. Yeah.
So can you
eh,
explain that part, previous one? Yeah, that
this one.
one two. Yes, sir. That 1 2 3 and 1 2 2. Is this the looping is allowed in the edge pair coverage or
No,
not?
so yeah, so what happens is for edge pair, what do you need? If you start from 1, I go to 2. So 1 2 and 3 is one edge pair,
Yes, sir.
right?
Yes, sir.
But I can also have 1 2 2 because edge pair coverage allows self loops. Okay, so
Okay.
1 2 2, but 1 2 2 is no longer simple. Is this simple? It's not simple, right?
Yes,
Because
sir.
right, so simple, what was the criteria for it to be simple? You had to start and end with the same one if you're
Same
looping.
one. Yes, sir.
Yeah, yeah. So that is not happening, and therefore it is not simple. And if not simple, by definition, it cannot be prime path, right? Prime paths are only simple paths, just that the longest prime simple paths that can be there. So prime paths are the longest simple paths, basically. Okay. So that is one way to remember this. And therefore you see one example wherein it does not subsume, like prime path coverage does not subsume HPR coverage. Okay. All right, so this graph is given, and it is said that there are 9 prime paths. So you see, once we compute that, maybe we'll see that. But it says 1357 skips the loop, right? So 1357. Okay, so I start with 1, go to 3, 5, and 7. So in this case, I did not went into the cycle, right? This part of 5, 6, 5, and therefore I skipped it. And at the same time, prime paths, another prime path I'll have of 1356 also, like a test path that yeah, in this case it's not a test path, it's just a prime path, right? Because for test paths you have to visit that, but I'll come to that later. So 1356 another prime path. Okay, and it says 1356, so it executes the loop once. You cover for that, right? Again, you cannot stop here, you cannot stop at 6. we are just saying that this itself is the test requirement. This is the prime path that you need to cover. This is the TR. Okay, to cover for it, to actually execute it, you need a test path. So how do we get test paths out of it? You have to extend it. That is the idea. Okay, so you have to make sure you construct a test path that actually has the prime path as a subpath so that you visit it. So for example, I'm starting from one, that is okay because I have to start with the initial node in my test path also. So I start with that, that's okay. I go to 3, I go to 5, and then I go to 6. So that is what my prime path said. Like prime path requirement was that I visit this 1356. So that is done. Now I have to finish the path, finish the test path. So I'll come back. I have to come back. So I'll come back to 5 and then I go to 7. So that is okay. In test paths, be careful with this. Okay. In test paths, there can be repeats of nodes. Like nodes can be repeated in test paths. Okay. It's just that prime paths, you cannot have repeated nodes. Okay. But once you construct the actual test path, not the test requirement. Okay. Once you construct the test path, there can be repeats. That's okay. That's perfectly fine because some things are inevitable because you have to finish at the final node. So once I am at 6, I have to come back and finish at 7 to be to be a valid test path. So that is okay. That in test paths, node can be repeated. Prime paths, nodes cannot be repeated. Okay. Be careful. And prime paths themselves are not test cases or your test paths. It's just that it's a test requirement that I wish to do similar to edge coverage. Okay, so prime path coverage is just that. So in edge coverage, we were having how much? What we were having paths of length up to two, up to one, right? Up to two rather. Yeah. No, no. Edge pair coverage we have up to two. For edge coverage, you have length paths of length up to one. That is okay. Similarly, prime paths just say that okay, these many test requirements you cover. I've given you that. Now you have to construct test paths out of that so as to actually cover for those requirements. Okay, so here we have just shown that what happens in these different prime paths. These are not as paths. In this case, however, 1357 coincides with being a being a test path also. That is fine. We'll consider this. This is also a prime path. This is also a test path. So that is okay. But this is not a test path. However, this is a prime path. So to make it a test path, you have to extend it. Okay, so that is the idea. All right, and then again 656 is so you iterate, you keep iterating so how many ever times you wish to do that. But in prime path, as we said, that it has to be simple. So for it to be simple, if it repeats, okay, so you see 6 is being repeated here, so only first and last has to be same, and that can be repeated regardless. Internally there should not be any loop. So this is also simple, also prime path. This is also simple, this is also prime path. That is okay. This is prime path and also simple, so that is okay. But this is not test paths. So to make it test path, you have to again extend it. So the requirement for test path is you start with the initial node, end at the final node. So how do I make this one into a test path? Maybe I have to start with one, so I'll start with one. So then the choice is mine. I can either go to 2 or 3. I have to cover this 656. Okay. So now I start with one because that is fixed. I have to start at one. Then I can go to 2 or to 3. So let us go to 3. I go to 3. So 1 3. And then I can go to 4 also. But if I go to 4, from 3, then I cannot cover for 6 5 6 because I'll end here. Then in that case, from 4 I cannot go, so I have to go 5. Then in that case, from 3, so 1 3 5, and then I go to 6. Then the prime path itself is there, so 6 and then 5 and then 6 again, and then I have to finish it again. So I have to, so I'm at 6 after covering for this prime path. I'm at 6, and then I have to come back because this is test path. So test path I have to finish it. So I come back to 5, and then I go to 7 to finish it. So the test path then corresponding to this prime path will be 1 3 5 6 5 6 5 7. Okay, is that clear? Any questions?
So, what is the difference between path and subpath?
Okay, so the path is that you have a larger path, let's say. So for example, the path that I just now mentioned, right? So 1 3 5 6 5 6 5 7. Okay, so that's a longer path. In that, you have several other nodes that are visited. Some paths which are inside of that. Like 656 is there, right? 656 is also there in that path. Maybe you can think about it like this. So 3 5 is a subpath of 1 3 5 6, right? Because 3 5 is in there, or 3 5 6 for that matter, or 1 3 5, or 3 5 6 and so on. So anything that is part of the larger path is basically a subpath.
And what is the difference between visiting and touring?
That is coming up next. Okay, so this next slide is actually
Okay.
going to discuss about that, you see. tours and side trip. Okay. Yeah, touring in the in the general sense basically is that is visiting in that case, but we'll have notions of side trips and detours also in the case of tour. Okay. So when we tour, we say it is in the subpath, therefore we visit. So either you say tour or visit, that is okay. That's not a problem. But then in tour there are two kinds of tours, two ways you visit something. Okay. I mean, one thing is just you visit, but the other is that how you are, you know, coming there in some sense. What is the path that you followed before that and after that? So that is what side trips and detours are going to mention. So slight distinction. It's very easy to understand. Maybe I'll describe that. Okay. So this part is clear, right? So subpath is basically when you tour it. In fact, yeah. So the touring definition is mentioned here itself, right? Tour subpath Q if Q is subpath of P. So that is okay. So for example, let's say I wish to cover for prime path, some prime path. Let's say I wish to cover for 1356, this prime path. Then I have to construct a test path which towards this prime path, which does like which follows this or which visits this path, which follows this path rather. Okay, so I'll have to have this. And what is the requirement for test path again? So I have to start with the initial node. I am starting it already with that. So it's okay, 1356, and then I have to finish at the final node for test path. Okay, so then I have to extend it. So I have to extend it, otherwise I cannot make it into a test path. So I'll have to come back. So from 5, I then from 6 I go to back to 5 and then to 7. So that is up to you how you wish to visit and complete the test path. But then you have to make sure that you, the the requirement, the TR, is actually a subpath of the test path that you have constructed. Okay, so we will see this. Prime paths by definition do not have internal loops. That is okay. Okay, yeah, sometimes it might happen that you might have internal loops also, right? Otherwise, it is not possible to, uh, you know, like it might be depending on the nature of the CFG that it is not possible to skip loops in some sense, right? You have to go through the loop and then therefore it creates an internal loop, which is not allowed in prime paths. Then how do we do that? Because otherwise it'll become infeasible, right? So then this idea of you know uh, yeah, repetition is allowed in the test paths. That is okay, but then there are ways by which you visit it. So two different kinds of touring is there. So I'll show you the general case. So for example, I have a test path, so I want to visit this one 1 2 3 4 5, which is also a prime path. That is okay. So I start from one because for test path I have to start from one. Then I go to 2 3 4 5. So notice the edges, the blue edges that are there, right? So I'm following this 1 to 2, 2 to 3, 3 to 4, 4 to 5. That is done. Okay. So then I'll come back to this definition later. Let us see the diagram that is mentioned here. So this touring the prime path without side trips and detours, so that is okay. This was the prime path, right? 1 2 3 4 5. Okay, this is the original path. Then this is the same path that I'm following 1 2 3 4 5, but there is a side trip that is involved in that. Okay. So what is the side trip? Side trip is that you are following your original path, and this is relative. Okay, the idea of side trip and detour is relative to some original prime path that you are having. Okay, so you have to have also some original path that was there, and then you in relation to that you determine whether that is going to be a side trip or detour. Okay, so because this is the path that I am trying to follow. Okay, but if it so happens that I do this 1 2 3, because it might be depending on the program that I cannot from 3 to 4 directly go from 3 to 4. Maybe I need to follow the loop. I mean it depends. Okay, but in general what happens in side trip is I went up to 3, then again additionally I visited something else. Okay, maybe 6, maybe something else in between, that is okay. But then I came back at where I you know the digression, wherever the digression happened, I came back to that. So from 3 I went to 6, and then I came back to 3, and then continued on my original path. So in the original path, it was 1 to 2, 2 to 3, 3 to 4, 4 to 5. In the side trip also, you have 1 to 2, 2 to 3, 3 to 4, 4 to 5. So all the edges are being followed still as the original path. It's just that I visited 6 in between, which is okay. But I came back at number 3 again and followed from there. Okay. What happens in a detour is, you might notice the difference here, is that you follow 1 to 2 and I go to 3, that is okay. This was supposed to be dashed, this arrow. And so I go to 3, and then from 3 to I again go to 6. But instead of coming back to my original path, I went on to continuing from a different route that is there, right? So I go to 4 and then to 5 from 6 itself. So in this case, you missed on the edge 3 to 4. Okay, you have you still followed all the nodes, because what were the nodes that we followed? I was visiting 1, I was visiting 2, 3, 4, and 5. That is the intention of the prime path. Okay, but then in the side trip case, I visited 1 to 2, 2 to 3, 3 to 4, 4 to 5. So again, all nodes are being visited, but additionally some other nodes are there, but that's okay. All nodes are still being visited, and all edges are still being visited as the original path. But in the detour case, what is happening is all nodes I'm still visiting. So I'm visiting 1, I'm visiting 2, I'm also visiting 3. I visited additional node, that is okay, but I'm visiting 4 also, and I'm also visiting 5. So that is okay. In terms of nodes, I'm still visiting all those things that I was visiting initially in the prime path. It's just that the edge 3 4 3 comma 4, this edge is not being followed. Okay, so that is what makes a side trip different, the detour different from a side trip. In side trip, you follow all the edges that you were following earlier. However, in a detour, you don't follow all the edges. Okay, so by definition, if you think about it, mm, then in that case, because detour just says that you have to visit all the nodes, right, that are there. So by definition, if you think about it, all detours are side trips. Rather, okay, I'm saying the opposite. All side trips are detours in that sense, if you think about it, right? But then there's additional criteria that you have to also, you know, come back at something different from where you initially diverted. So you started at 3, you went to 6, and then you, instead of coming back to 3, you went somewhere else. So that is what a detour is. But you're still visiting all the nodes. So in fact, we'll go back to definition maybe and quickly see that. So it says the test path, this is side trip P towards subpath Q with side trips if and only if every edge in Q is also in P in the same order. Okay, this must be clear with the diagram also. Right. So again, side trip, if every edge is being followed, as was the case in the original prime path, then you say that that is a side trip. Maybe that there are some additional nodes that are there in between, but that's okay. If every edge is there, then you say that this is side trip. In detour, however, this is like it is path P towards subpath Q with detours if and only if every node in Q is also in P. So we are not talking about edge. Okay, this condition is slightly relaxed in that sense. We just say that okay, you visit everything, but you need not follow the same path or same route that you followed in the original path. So you might digress a little bit, but you have to again make sure that visit every node. That is a detour. And then again, this is one more thing that is mentioned here. The tour can include a detour from node n as long as it comes back to the prime path at a successor of n. Okay, so this part is important of being ending up at a successor. So for example, in this case, what happens is, you see, you were supposed to come back to 3, right, after going to 6, but you went on to 4, which is actually a successor of 3. Okay, so that is what makes it detour. Is this part clear? Any questions on this? Okay, all right,
No, sir, it's okay, sir.
fine, fine. Thanks. Thank you. And yeah, so it says some test requirements related to graph structural coverage can be infeasible. It might happen. So then in that case, what do we do? So we say we follow the approach of best effort tutoring, which says that we satisfy as many test requirements as possible. So infeasible requirements, if there are any, we can possibly ignore it, right? Because I mean, something is there which cannot satisfy, then the rest of the requirements that are there, right? Maybe you try to satisfy that. Okay. Yeah, round trip path is basically similar to a loop. Okay, so a prime path that starts, but this is a prime path. Okay, so again, the notion of being simple is important here. It's a simple path that starts and ends at the same node, right? So it's a simple also, but it's a round trip, meaning 3 to 3, 2, 3, 2, all such paths, right? Wherein you start from somewhere and you end at the same place again. And simple round trip coverage, it says TR contains at least one round trip path for every reachable node. I mean, wherever you have round trips, yeah, like there can be multiple round trips, right? So but then you make sure that you contain for each reachable node that is there, uh, if at all there is a round trip that is associated with that node, then you make sure that you include at least one of the round trips that is actually originating at, in some sense, originating at that node, right? So for example, if I'm at 3, then from 3 to 3 there is this loop that is there, so I ensure that I cover for that. And similarly, a complete round trip coverage says that test requirement will be basically all round trip paths for each reachable node. So simple round trip is that you make sure that you cover at least one of the loops, right? That is there. And complete round trip coverage would say all the round trips that are there for all nodes that are there. Okay, so that is what there is to it. Yeah, and you might understand that since we're talking about round trips only, no. So in that case, it says omit nodes and edges that are not in round trips, meaning this idea of starting and ending at the same node, no. So it might happen that some of the nodes might not get covered in that way, right? And it might be that some of the edges are not covered in that way because I have a restriction saying that to start with one node and end at the same node again, right? So that kind of a round trip has to be there. So in that case, of course, it might be that some of the nodes and edges will be missed, and therefore they are not going to subsume this round trip coverage. Actually does not subsume edge pair, edge or node coverage. It might, but we cannot say in general it is subsuming that because we can have examples wherein it does not. So therefore, in general, the conclusion would be that it does not subsume. Okay, so this is what you have to remember for graph coverage criteria. We have complete path coverage, which again in practice infeasible because of loops, right? So loops, you have infinite paths which you cannot have, therefore complete path coverage is infeasible. But if you do that, of course you do prime path coverage also, because every path you're doing, right, every combination in some sense, but that isn't feasible. So we do prime path coverage, and you see prime path coverage does a lot of the other things also. So except edge pair coverage, it does cover edge coverage also. So if you do prime path coverage, you are subsuming edge coverage, you are doing node coverage also. Similarly, if you do edge coverage, you subsume node coverage. So this is how to read this graph. If you are doing edge pair coverage, then you also satisfy edge coverage implicitly and node coverage implicitly. If you do prime path coverage, then you also implicitly satisfy complete round trip coverage because you do it for every node that is there and all the round trips that are possible. Therefore, you satisfy complete round trip coverage. And if you do this, of course, by definition, simple round trip coverage is also subsumed. Okay, so this graph is important. It kind of summarizes all the coverage criteria in the graph model that we have. All right, so this is what we have. Yeah, regarding the example of you know prime path coverage, we have taken it so many times, so we have a recording also of prime path, how to compute prime paths. So maybe I'll share that one. Okay, so with this, maybe we can close.
So the session will be around 8 to 9 every day.
No, no, no. It is on Tuesdays, no? Every Tuesday, 8 to 9 is what we have.
Okay.
Yeah. All right. Any other questions that you would like to ask, or else I can close for today?
No, sir, it's okay. My side.
All right. Okay. Then thank you all for attending, and we see you in the next one. Thanks.
Thank you, sir.